it's my great pleasure to introduce our work, Dynamic PlenOctree for Adaptive Sampling Refinement in Explicit NeRF. Here is my teammates, including me, Haotian, Yiqi, and Professor Yi Zhe and Professor Edison Ning Wang. We are from Hong Kong UST Guangzhou Artificial Intelligence Trust. NeRF has gained considerable interest for its efficient training and fast inference capability, making it a promising direction such as virtual reality and gaming. The NeRF training progress can be described by the diagram above. For instance, giving a range of RGB streams from different viewpoints. NeRF aims to reconstruct 3D objects like the logo by integrating a group of nodes within the real box intervals by volume rendering. In details, it inputs the spatial coordinate including x, y, z, and ray direction theta and phi to infer each point's RGB color and density sigma. Then, the volume rendering takes those properties by rendering them into RGB values and supervised by the corresponding ground truth color. Real-time NeRF has tracked a wide range of attention for its fast rendering speed for interactive experience. PlenOctree, for instance, has reconstructed 3D object using the octree structure, which largely enhances its rendering speed by skipping the sparse intervals within the octrees. As we observe in our experiments, there always exist artifacts that occupied in the octree structure, bringing unnecessary memory consumption and dampened rendering performance. The problem is aroused by the reconstruction process that takes the dense samples from pre-trained NeRF-SH octree reconstruction directly without further modification on the cache color and density. Specifically, instead of dropping the various regions directly, we propose dynamic PlenOctree that aggregates these values progressively during training progress. Our tailored operation, including sampling and pruning, along with our dynamic calibration procedure, has provided more compact structures, as shown in the example scene of a chair. The fact is also proven by the hot dog scene on the right. In detail, our dynamic PlenOctree consists of two core components. First, we take the pre-trained NeRF-SH or POT modules into our later modification process directly. Then, we modify it based on our proposed signal-based region identification method, which consists of our tailored sampling and pruning operation guided by the training signal S throughout the training process. Next, with the ray signal guidance, we fuse the hierarchical octree feature by pruning and sampling operations, instead of dropping them directly throughout the learning process. This keeps the whole octree parameter intact, while ensuring it learns continually. Overall, our pipeline consists of three parts. The last part, parameter stabilization, is aimed to stabilize the learned parameters with the color supervision. And thus, we iteratively execute the three components to obtain the final result. In summary, we address the limitation of the fixed octree design in POT, and we are inspired by seeing complexity actually evolves continuously with the updates to the cache color and density. We solve it with the signal-based region identification along with the octree feature fusion algorithm. But we cannot reduce the excessive training time for its predecessor, NeRF-SH. We may enable model training from scratch by methods such as reinforcement learning in the future, or adapt the signal-guided modification method to other datasets.